Bueno, buenas tardes, bienvenidos a la conferencia de hoy.
Good afternoon and welcome to our lecture. We're deeply
we
would like to grateful because in spite of the football game, you're here. The conference today is going to tackle a very interesting subject, our project on the CLIC, which is the Compact Linear Collider. It's one among the possible projects for the future after the Large Hadron Collider. And this is within the framework of our cycle of conferences organized jointly by BBVA Foundation, CERN, and the Secretariat of State for Research, Innovation and Development. So, this is why I'm going to introduce now, I'm going to elaborate a little bit on the subject. Why do we have to go for new linear colliders? First of all, as I said before, I'd like to thank the organizers of the cycle. I'd like to thank BBVA Foundation, the CERN, and the Secretariat of State for Innovation and Development for this kind of invitation. Perhaps you're familiar with the subject, with the standard model and the definition of what we do, our theory, the theory underlying the laws and the behavior of elementary particles, but allow me to make a short introduction on the model. The standard model, as you know, we have three main pillars, and we have here the particles, elementary particles. Those are like bricks. Those are like the elements, the smallest elements, and the matter is made up. And we see here by leptons, quarks, the up, the down quark, as an example, and those particles, leptons and quarks, are, as we see, constituents of the ordinary matter. The other pillar, fundamental, is the way particles will interact one with another. And we have interactions. In the case of a standard model, we have electromagnetic interaction, the weak interaction, the strong interaction, and then gravitational forces. In the world of particles, it hasn't been checked, confirmed. We haven't seen phenomena due to the interaction. We have here the two main pillars, and also we have a third pillar, which is fundamental, which is the one of symmetries. And the standard model is based on interactions, based on symmetries, internal symmetries that mean that we have invariant fundamental laws under several types of transformations. Those are fundamental pillars for constructing or proposing theories that will be robust, according to which we could predict new phenomena and make calculations. But symmetries will have an effect, which is that symmetries won't get along well with the mass. Or for that, it was necessary to define something, to invent a mechanism, which is the mechanism of spontaneous breach of symmetry. So it is the EWSB, and we have here, we could preserve the theory, the behavior of symmetries, and particles could get a mass. And this introduction of the mechanism at the same time made us predict a new particle, the Higgs. Higgs particle is not a quark, it's not a lepton, it is not a boson. I haven't introduced bosons. Each force, each interaction will have a boson associated, which is the one that takes care of the interaction, like the mediator, and then the Higgs. And here we don't see a boson, and this is not a boson. It's something odd, something different, something that was predicted according to the EWSB mechanism. For more than 50 years, Scientists have been looking for the particle that was finally discovered the 4th of July 2012. Well, something like the particle, something compatible with the particle was announced, was presented. But once discovered the particle, the next step is to understand what does the particle mean, to see if this is exactly what was predicted by Higgs. I mean, the Higgs boson, according to the Standard Model. Back in 2012, there was a cycle, I think, here, organized to give a technical recognition to this discovery, and you see all the media presented results. After years of this discovery, that was only the beginning, and now we will say H1025, Higgs H125. Let's see what we've discovered. Let's look for the properties and try to understand the properties. What we've checked is that the particle behaves like what we could expect according to what's predicted on the Standard Model, but essentially we have to keep on investigating, keep on researching to know more on the particle, getting more out of what the particle is teaching us. We don't know if this is what was predicted within the Standard Model. We don't know if this is an elementary particle or if it is a particle with an inner structure. We don't know if it is unique or if there are very many Higgs particles. Supersymmetry will predict lots of Higgs particles with these properties. So perhaps we've discovered the first particle regarding supersymmetry, and for that we need to perform more tests, experiments. But that was only the beginning. So the one that's giving mass to all particles, it is what we know technically to know if it is responsible for this effect, and then we have to know if it is due to quarks or due to other mechanisms. What we think about mass coupling relations, we think about matter-antimatter, and there could be implication in the inflationary expansion of the universe. We have to know this, we have to see if this is related to matter-antimatter asymmetries, and we have to think about if it is produced by quark tops or another mechanism implied new particles. We need to answer to those questions, and then we need the Large Hadron Collider data collection system, and that we also need, as our lectures will present, we need new accelerators able to be accurate enough to give an answer to these important questions. Allow me to introduce another aspect regarding the Standard Model, which is relationships with the mass. And then back in 1687, Newton, as we see, that started back there, when Newton introduced mass as resistance to movement, inertial mass, and out of which we had gravitational laws stemming from that. And then it is, as you see here, force equals mass by acceleration. And then after that, Einstein told us that mass and energy were manifestations of the same thing. Those were equivalent things. So the mass was introduced as condensed energy. And then in this mechanism of the EWSB, we see here that Brout-Englert-Higgs established a connection with the vacuum. Vacuum is the state of a minimal energy. What have we discovered back in 2014 with measuring the mass of a Higgs boson and the mass of quark top? Now we're living in this metastable universe. Perhaps our universe is not stable as we thought, and we are at a metastability state. That means that at a given point in time, there could be a disintegration. So are we going to give it a thought? I don't think, it's going to happen tomorrow. I think we'll have time to retire. It's not some of an added risk. Well, but I think those are problems of our standard model, telling us where the problems are, and it is necessary then to propose a new theory to explain this, introducing terms to get rid of the lack of consistency. And then there is another physics, another limitation, and I think that you might give it a thought. And you all know the existence of dark matter. Back in the 30s, it was seen that the orbit velocities, the orbits were not, the speed was not corresponding to the mass of what was visible. So there should be a mass, non-visible matters, something we couldn't observe that would be responsible for the movement. And then those elements were confirmed, and we have this dark matter been confirmed with very many different experiments and beautiful experiments using gravitational lenses. In the standard model we have nowadays, we do not have a natural candidate to explain dark matter. So if there were limits to our standard model, then we would need a model or something to add, something to explain this. After many years, there were programs conducted with success. Lots of resources have been invested, lots of accelerators were created globally, and now we have the discovery of a new particle, the H125 Higgs particle, and then we're discovering now the limits of our knowledge, so the frontiers of our knowledge, and that opens new gateways towards being aware, knowing more, and having a better definition of our future objectives. So our fundamental questions, for developing physics of particles, is what about the mass of the Higgs boson? Is it elementary or is it a compound mass? How about the mechanism regarding the breakage of symmetry? Do we have one Higgs? Do we have many Higgs? How about the stability of the universe? How about the nature of the dark matter? How about the inflationary theory of the universe? And how is it so that there is only matter at the universe? We have different tools to study our properties. We see here the Higgs 125, the quark top, bosons W, boson Z, the gamma, and the search for new physics, new particles, and that's very important. We have here the Watson, and we have here, it's very important what we see here. We have here new accelerators, and what we need is new accelerators. We have new accelerators, we have new ideas, new projects like the collisions, proton collisions, or the positron-electron collision, electron-positron collision, or proton-proton collision. The Large Hadron Collider is proton-to-proton collision. And then now we have the Large Hadron Collider that's operational, and we also have, and it's been approved last week, recently approved, as I said, we have phase 2 of high luminosity tests, and there is a proposal for a new accelerator, and that's food for thought. It's going to be presented here, the future accelerator, the circular collider. The circular collider with this energy you see here, we have the proposals and projects been already established for the future. And here we have linear colliders, that's what the two next speakers will elaborate on. Then we will have a circular colliders, and then they are not all equally mature. They have been developed, we're understanding technologically the possibilities, and the International Collider, for instance, consists on, they have all the technical requirements, so it is an accelerator, it's a machine that could be constructed because we only need money for that. If the funds were allocated, we could do it. We also have the CLIC, the Compact Linear Collider, which is the proposal made by CERN for this type of accelerators. It is a subject for today's lectures. And we have here the conceptual design also, and regarding preliminary aspects, we have also the circular colliders. One was proposed in China, by China, another one proposed at the CERN, same line of thoughts with the Large Hadron Collider. And prior to putting an end to my presentation, I'd like to mention that in Spain we have great efforts conducted along the line of thoughts in order to work together, in order to go along the line of studies, to have then the possibility for new accelerators. Spain, we're working hard in Spain. There is a network, a future collider network, and we have here the possibility of exchanging communication, ideas, different groups, and giving token recognition to mutual cooperation, exchanging information. We have here detectors, we have here studies regarding physics, but also we have industrial interests. I'd like to mention here some of the groups having worked on that and put an end to my presentation. Allow me to introduce two real milestones, two real really excellent speakers who are going to elaborate on the CLIC project, the compact linear collider, Dr. Steinar Stapnes and Dr. Lucie Linssen, both from CERN. Dr. Steinar Stapnes is director of the study regarding compact linear colliders at CERN. Dr. Lucie Linssen is the head of the group conducting the study of detectors and colliders, physics, and they need no introduction, but Dr. Steinar is the leader of CERN in research and development projects regarding the compact, the International Linear Collider, PhD, Oslo, 91, full professor since 1995. We've had the pleasure of working together. We know each other for a long time. We have the different projects, Delphi, Atlas, and CLIC, and he has also made fantastic contributions. He has been the president of the Norwegian Society of Physics and been a main researcher of different projects at the European Union. He has been leader of Atlas, leader of the Secretariat of the Council of Strategies within the CERN for the follow-up and application of the European Strategy of Physical Particles. And now Dr. Lucie Linssen, PhD, Amsterdam University, back in '86, has participated at many projects for developing detectors. NOMAD, for instance, is one of the experiments with neutrinos, and she's been the main researcher for fundamental projects. She's been a leader of many projects for cooperation, and now she is the leader of this project regarding the detectors of the CLIC. And now, Professor Steinar Stapnes, you have the floor, sir.
Good evening, everybody. The seminar today is about the Compact Linear Collider, CLIC, which is one of the future projects being evaluated for potentially being implemented at CERN after LHC. As you know, today at CERN, we are all busy. We're operating LHC, which is a 27-kilometer circular collider, but CLIC is a linear collider. So if you look at this picture from Google, here you see the footprint of LHC, the 27 kilometers, and here you see a long line with 3 different colors, which would be the 3 possible implementation stages of the CLIC project. So, and the natural start of that project will be something like a 10-kilometer accelerator, then being expanded over a time period of something like 25 years up to 50 kilometers. So the total length of this is a 50-kilometer accelerator. And here you see an artist's impression of how this would look along the foot of the Jura Mountains here, which, of course, this is also something like 100 to 150 meters below ground. Now, why do we build accelerators? This is of course, we do that to study our universe, and we try to study the universe in various ways. But accelerator is a particular powerful tool. And they are expensive. They are the biggest scientific instruments, I believe, we have today. And the reason why we find them so useful for us is that we believe that the universe has developed from a big bang, very quick expansion into the universe we know today, over something like 13.7 billion years. And by colliding particles in an accelerator and using Einstein's formula, where we can go from the mass of these particles into energy and create new particles, we can create all kinds of particles at very high energies. In fact, we go back to energy density, which happened something like a millionth of a second after the Big Bang. So we go back and study our universe at close to the start of the universe. And this tells us and gives us constraints of how the universe looks today. There's other aspects of accelerators. We live on a scale of something like meters or kilometers, but the universe we know is incredibly big, and we study the universe in many different ways through also large instruments, telescopes, and all kinds of instruments looking at the radiation from the sky in different forms. On the other scale, we also need big instruments. We go from glasses, magnifying glasses, we go down to microscopes, and we go down to accelerators. And the reason, and by doing that, we go down in scale. So we study matter at its most fundamental level, at what matter is really built up from. And we study how these fundamental parts of the universe interact. So it tells us about matter itself and the interactions between matter on a very fundamental form. And the reason we can do that is that the wavelength, as you know, a particle or a fundamental particle is both a particle and a wave, and the wavelength is decreasing when we go up in energy. So if you have higher and higher energy, we get a smaller and smaller wavelength, and we can study the matter down to 10 to the minus 18 meters. So by doing that, by building this accelerator, it allows us to do all these kind of investigations in a controlled way. We create these particles, we collide them, we see what comes out, we see how they are constructed, and we see how they interact among themselves. So then the question is, what are the best possible accelerators? And there are many different opinions, but what we're going to talk about today is a linear accelerator colliding electrons and positrons. In fact, there are not so many particles we can accelerate. To accelerate a particle, you need a particle which is stable, because you need something which doesn't interact and is split into parts right away. And in fact, the choices made are usually to use a proton or an electron. So in fact, in the hydrogen atom, you have the two. We know it's a stable construction, and the proton and electrons are both stable. Of course, we can consider using other ones, but these are the most used by far. Now, the proton collisions are quite complex, because a proton is in fact quite a complicated package. It consists of quarks, particles interacting between the quarks, and there are also antiquarks popping up. So if you collide a proton with a proton, you collide two quite complicated packages, and Lucie will come back to that in her presentation, more about the difficulty of that. So on the other hand, if you go for electrons, we have to collide electrons and positrons, because we want to create something which is neutral, and this is a particle and an antiparticle of each other, and these are fundamental particles, so they are not consisting of any other particles, as we know it today at least. So we have a well-defined initial condition, we have a well-defined energy, and we also have less background. So clearly that has many advantages. We do have a machine colliding protons, LHC. So obviously in the science of particle physics, I think there's a full agreement at least that we need an electron-positron accelerator to be able to move forward in our research. Now, how do we control the particles? So I'm afraid I have to put up a formula for that. but the formula is a fairly simple one. It's the force acting on a particle with a velocity v and a charge q. So we need a charged particle moving along at a certain velocity. And if we expose that particle to an electric field, we can obtain acceleration, or to a magnetic field, we can bend the particles. This is coming out of this formula. So, in fact, the reason why we cannot use magnetic fields to accelerate the particle is that this formula tells us the magnetic field will act perpendicular to the speed of the particle, and we will not be able to increase the speed. So to increase the speed of the particle, you have to use electrical fields. And we have to use the largest possible electrical field to get the largest possible acceleration. To deflect it, we could use both electrical and magnetic field, but it's just much easier to create large magnetic field, so we use magnetic field. And how do we do that in practice? Here you see two elements used to accelerate particles. So these are, I will come back to this structure, which is a CLIC structure. This is a different structure used for superconducting machines. And here you see two magnets. This is the magnets we used in LHC, which bend the particles around the LHC. So it's a so-called dipole magnets. This is created by the highest possible current, and then you get a magnetic field through the coils of electrical current. And they are superconducting to get the highest possible current, because then we get the highest possible magnetic field. And this is a quadrupole magnet, which is focusing particles. So we do not only bend the particles, we also focus them, because what we are looking at is not a single particle, but groups of particles, which comes along at a certain distance. And there are roughly like there's a billion particles in each package. So this is how we do it. We take a stable particle, electron, positron, proton, most used, and we steer them with the help of electrical and magnetic field. And then it's a question of technology. What is the best technology to use? And what gives us the best possible accelerator at the end? Now, I will going to talk about electron-positron accelerators. And for electron-positron accelerators, we have a particular limitation. But in fact, there's a phenomenon called synchrotron radiation. And this is loss of energy when you bend the particle. So if you bend the particle like that, it will lose energy. And at some point you will be limited by your acceleration cannot put in more energy than is being lost by bending it. This effect is described by this formula and is increasing very quickly with energy, but it's also proportional to 1 over the mass to the 4th power, telling us that this is a particular significant problem for light particles. And it happens that the electron is a factor 2,000 lighter than protons. So this is a much bigger problem for electrons and positrons than for protons. So if you want to study in detail particles in collisions with electrons and positrons, you reach the conclusion that as you go up in energy, if you try to bend them around a ring, you have to expand the ring enormously. So you have to increase the radius to compensate for this loss in radiation. So the cost of such a machine as you go up in energy just takes off, it explodes. So if you want to go to high energy with electrons and positrons, you have only one choice, you have to go to a linear accelerator. And of course, in this region, you can dispute which one is the best. So this is much less of a problem with protons, but it's also going to be a problem if you go to really high energies in a proton ring at a certain size. Because the only way to compensate is to go for a very large ring, and then also the cost there will increase. But for protons, you are more limited by the magnetic field to keep the particles going around in a circle. So now I'm finally to the linear accelerator. So we got to the linear accelerator by wanting electrons and positrons, and by the fact of radiation losses, the linear accelerator is the best, or in fact the only option. So now I will go into the details of such a, I will go into the main elements of a linear accelerator. So this is a generic linear collider, and let's start with the electrons first. So you start with electrons, and in fact, you don't start with a single electrons, you start with groups of electrons. And in fact, in CLIC, you have trains of particles, and inside these trains you have groups. And inside each of these groups you have 10 to the 9 particles, so a billion electrons. In fact, 5 times 10 to the 9 particles. So you have these groups of particles coming along, and you have to make them all behave in the same way. To do that, you put them into what is called a damping ring. I will explain a little bit how a damping ring works. Then you have to transport them to the end of the LINAC, and then you accelerate, and you accelerate as much as you can, because you only have one chance. These particles pass not as in a circular accelerator many times, they pass only once. So you accelerate as much as you can, and then you want to have as many collisions as possible, because even though you have a billion electrons there and a billion positrons there, when they collide, it's very difficult to get a real, they get close enough to have a real interaction. So you make the beams as small as possible. So you squeeze them in something called the beam delivery system. And this is a formula for the intensity, and I don't want you to understand that formula, but there are two key elements of getting this size of the beam as small as possible. One is that the particles from the start are behaving in a uniform way, like a fish school. They all move the same way. And then that you manage to squeeze them with the help of focusing magnets in the last, in fact, several kilometers. This little thing here is 2-3 kilometers long. So that's the key for getting the intensity up. So the key elements of this is to create what we call low emittance beams here, and then transport this well-behaved beam to the main LINAC. And of course, you have to do the same for the positrons, which is in fact more difficult, but I will not go into that. Then you have to accelerate. So the key parameter here is the energy increase per length. And then you have to supply the energy from the wall. You need a lot of energy, you need megawatts of energy, as efficient as possible to the accelerating elements. This is a key difficulty for any accelerator. And for CLIC, we have to take a particular solution for that, which in fact also many other accelerators are going for, is to have another beam intermediate to deliver this power. And then the fact is that you create these extremely small beams at the end, you squeeze them in the beam delivery systems. So that's the key elements, and I will show a couple of slides for each of these challenges. So the first thing is the damping ring. And there we use the experiments for what we call a light source. A light source is an electron ring, I will show it a bit later, which is used for a different purpose. It's used by manipulating the beam to create photons, and you use it to study materials. So what you do there, you have a particle which is not behaving absolutely correctly, is not moving along the axis of the beam, is moving a little bit like that. Then we call it wigglers. This is magnetic fields oscillating. You reduce the energy of that particle, and then you re-accelerate. And then you get a final particle which is more going in the right direction. So that's the basic principle of the damping rings. And here is an example of a light source, in fact, is the ALBA light source in Barcelona, which is basically such a ring. But as I said, it's used for a different purpose. They inject electrons, they send them around in an electron ring, and then by bending them and manipulating the electrons, you get photons, and then you do all kinds of studies of materials in this ring. And here you see it in real life and inside. So in fact, in the CLIC project, we work with the team at ALBA, which do studies for this damping ring in general, including this acceleration system, which is needed to create this well-behaved beam. And we also do a study of something called an extraction kicker, because in our case, we will take that beam at some point and kick it out of the ring and into our main straight linear accelerator. And this is done with a collaboration between CERN, ALBA, but also EFIC Valencia has been central in the development of this device. The next difficulty is related to power. So in most accelerators, the power is in fact coming from something creating a pulse, and then you have a high frequency klystron it's called, which modulates it. So we have in our case, we need a 12 gigahertz frequency. And these are little accelerators on themselves. And the difficulty with this method is that you need, in the case of CLIC, you will need something like, even for the initial stake, 8 kilometers of these devices. And they're very expensive. We are talking maybe a million Swiss francs per piece, and 8 kilometers of that. They have a lifetime which is limited, so they will always have some of them breaking. So in our case, for CLIC, we have chosen another method. But generally, we also use them in a more sophisticated way to create the power. Then we put that power into a structure, and we make sure that we get an oscillating electrical field inside this structure, and we make sure we pass the particle in phase with this oscillating wave, such that the particle, when it goes through there, electrons one way, positons the other way, they see this wave and they get a kick. And the key is to get them the maximum possible kick. So it's a bit like a surfer on a wave, which gains speed from the wave. So how do we do that? What is the maximum we can do? Here there's a bunch of technologies, but what we have decided to use for CLIC is what we call a warm technology, a room temperature copper structure. With superconducting structures, you don't go so high in accelerating gradient, but it has other advantages. But for CLIC, we have decided to use work in this parameter space, which means that we have to have short pulses, because we put in a lot of power into a copper structure and it will heat up, basically. So there's a limit how long the pulses can be, and that's why we have this fine structure of half a nanosecond, and so on and so on. So it's all driven by the maximum acceleration we can get per meter. And this is the structure. It's built out of disks, extremely precisely machined disks to micrometer level. They are stacked up and they're put into a structure like that. So this is roughly, as you see, 25 to 30 centimeter long, consisting of 26 disks in this direction. And then we pump power into them at 12 gigahertz, and the particles go through in a ring in the middle, in a hole in the middle of these structures, this little hole here, and we put the maximum electrical field into there, limited it by how much the copper structure can handle of fields. So here is a little example of that. Assume you are a particle coming here, you see this field here, now pointing, you get a kick here, you move along, you get a kick here, you move along, you get another kick here, and so on. So as you move along, and if you do the frequency and the phasing correctly, you keep accelerating these particles faster and more. Now, how mature is this technology? These are the institutes in the world which either build these kind of structures, they are in green, or are able to test them. Because to test them, you have to put a lot of power into them and run them for a long, long time to see that you don't have discharges on the surface of these structures. So the key for building the building capabilities is this, which is an industrial capability. This is made in industry and in some cases assembled in these institutes. And the testing capability is big power elements. It's a klystron, as I showed earlier, which pump power into this structure, and then we measure the behavior of this structure. And also here, Spain is significantly involved. CEMAT here in Madrid, together with a company up in the north, DMT, are working on a prototype for this accelerating structure. That's why Spain is there. And in Valencia, one is building up testing capacity, a system similar to that, but not for CLIC, using the technology from CLIC, but it's really done for structures, accelerating structure like that, slightly different, with a different frequency, which we'll use for hadron therapies. I will come back to that later on. Then finally, we have to think about how to get the power in. And there we have to do something special, because as I tried to explain to you, to just pump the power in, as is done on a conventional accelerator, do not work. We will have too many failures, it'll be too costly, so we have to do something else. So what we introduced in CLIC, so this is the CLIC accelerator, main accelerator, like this. We have, and these beams are created on the surface, they're sent down, they're turned around, they're sent down and turned around. But we have a second accelerator. We have what they call a drive beam, which is shown in red here, and we amplify that beam. So this is very high intensity beam, a lot of particles, but low energy. And then we amplify it further with the help of what we call combiner rings, and we send it around here and we turn it around like that. So in fact, for a certain length here, the drive beam goes parallel to the main beam. And then we extract the beam, the energy from this intense beam into the main beam. And the reason we do that is that to get, with klystrons, beam into the drive beam is very efficient because we have very long pulses and we have a structure of the beam which is well suited for that. And if we need to increase the energy of the accelerator, we don't need to do anything with that. We just made the pulse longer so we can have one more group of particles going there. Here you see the depth profile. Here's LHC, and you see CLIC below that along the side of the Jura Mountains. So this is the implementation of it. And in fact, this is the trick we do with this drive beam. So we have a long pulse like that, split into 24 different groups of pulses, and we take 23 of them and we put them inside that one. So we increase the frequency inside that pulse by a factor 24, and we increase the intensity inside that pulse for 24. And then we send one pulse here, and we send one pulse there. So we send them along to the different parts of the accelerator. So this means that we have to have a power extraction unit and move the power over to the main accelerator. And all this is to have a higher power efficiency and to be able to have a machine which is easily expandable, because you can do that, as I said, by making this pulse longer. So here you see the drive beam going parallel, transferring in a copper structure power into the main beam. And in fact, here you see a simulation of what's happening. So here you see this drive beam coming into this power extraction unit, and you can notice the time scale here. This is within 3 nanoseconds. In fact, the pulse length is 240 nanoseconds. So it takes something like 70 nanoseconds to build up a good acceleration field in this structure. And then we've come with the main beam and pass it through synchronously with this RF power, as we call it. We call it RF because it has the frequency, it's at a radio frequency, but there's no deeper meaning of that than it's a certain frequency range. So here you see the pulses being built up. And in fact, if you keep running this film up to 70 nanoseconds or so, you have conditions in this main accelerating structure which is suitable then for the main beam. Okay, we have tested this concept. In fact, it's the key concept of CLIC in some ways to get the power efficiency. And this allows us to go to higher energy. And so we have a test facility where we create a drive beam with a combiner ring, and we send them into a test area where we have a main beam, and we have a module to test all this concept. And we have proven that, in fact, the limitation of this technology is not really coming from here. It's coming from the fundamental limits of electrical fields towards this copper structure. So we can get significantly higher energy kicks than what we need for CLIC, in fact, with this method. Here you see this exactly this type of structure, a drive beam transferring energy to the main beam. And as I said, we want to be at 100 megavolt per meter, which is a measure of how much we can accelerate. And then finally, nanobeams. These beams are extremely small when we combine them, collide them. In fact, we want them small in both dimensions, but it turns out to be more profitable to be small in one dimension and slightly bigger in another one. So in the vertical dimension, the beam is 1 nanometer wide, which is the size of a water molecule. And in the other dimension is 40 nanometers. The beams in LHC and many other accelerators are still very small. They're like a hair. For those of you who have hair, you can take out a hair. And this is what we collide. We collide two hairs, which are roughly a few centimeters long in LHC. But in CLIC, the situation is much worse. We have to collide water molecules, a bit wide water molecules with water molecules, after accelerating it for 25 kilometers. So this is very, very difficult. And of course, this is an important R&D. So what we do to solve this, first of all, we need to align all components of the machine and this, of course, we can test. We build a test set for that. And I will show the pictures of how we do that. We have to control and damp vibrations. In fact, the Earth is shaking wherever you go, even down in the tunnel. And you have to make sure that these vibrations are in a certain frequency range are not transmitted to the accelerator elements, so we can test vibration systems. Then we measure beam positions. We have to measure where the beam is and either move the element or steer the beam to make sure we know exactly where it is. And this is an example of measuring with the help of these couplers on the surface of a structure where the beam is, because you get an electrical signal depending on where inside the beam, inside this structure, the beam goes. And then we have a lot of algorithms for measurements, beam, components, optimization, and feedbacks. And then we test them in small systems, relatively small system compared to CLIC, to make sure that we can really collide this type of beams. So now I think I come basically to the end of the first part, and we will move with Dr. Lucie Linssen into detector and physics. And then I will come back at the very end. I will show a few slides about how we use this type of technology in other type of accelerators, because obviously when you push technology, this opens possibilities in other areas. And I will talk a little bit about the timeline of how CLIC could be implemented. So just to illustrate the point again, this is not done by CERN alone. It's done by a collaboration of something like 50 institutes and all over the world. And you see the countries and flags of these different institutes here. Then I stop and give the word to Lucie to continue.
Thank you very much for inviting me here. I think it's a big honor to be here and also to see that there's foundations that do help fundamental science, and it's a real honor. So I will continue telling you a little bit more about the electron-positron collisions and about the detectors that we use to study these collisions. So we'll start and repeat a short introduction on the physics, again compare proton versus electron colliders, say something about particle detections, what a CLIC detector will look like, something about detector technologies that we are developing for this collider, and then I will give a snapshot of what CLIC can really then do for all our physics questions. So this presentation obviously is possible thanks to the material provided by my colleagues from the CLIC DP, from the CLIC Detector and Physics collaboration. Okay, so we're back on the elementary particles and interactions. So what you see here is again the list of all the particles that we know of, the elementary particles that we know of. And these consist of quarks and leptons, each in 3 families. Then we have a number of particles that carry the forces, strong nuclear interactions by the gluon, electromagnetic interactions by the photon, and electroweak interactions by the W and Z particles. And then there's, of course, the Higgs. Many of these particles have been discovered decades ago, and in the various accelerators, we have been able to measure them extremely accurately. Sometimes we measure phenomena to a precision of a per mil or even a millionth of accuracy. But this doesn't hold for all of them. And funny enough, we lack accuracy on the heaviest particles, because those are also the particles that we discovered latest. And it's these heaviest particles that are our best messages of new physics. So anything beyond the standard model that we know will be shown by the behavior of these very heavy particles. So for any next accelerator, and of course also for the ILC, we are after these heavy particles to tell us how they interact and to a very high accuracy. Now in this scheme, one can also still make a distinction when draw a line here. On this side, we have particles with a spin 1/2. We call them fermions. And on this side, we have bosons with spin 0 and 1. And these particles behave quite differently. And this is, of course, used in our research. And there's huge differences in mass between the various particles. The neutrinos carry almost no mass, and there's a huge scientific program specifically for neutrinos ongoing. Okay, coming back to the Higgs. So the Higgs is quite a special particle. It's a cornerstone of our standard model of particle physics. It's the particle that we have been looking for a very long time. It's very new, and it needs to be fully understood. As it carries, first we have to confirm that this is the Higgs and it behaves like the Higgs as we predicted it. It's, moreover, the only particle with spin 0, so it's quite different from the others. And it's the Higgs field, it's the Higgs that gives masses to the other particles. And the Higgs coupling to any other particle is proportional to the mass of that particle. Now we can study the coupling of the Higgs by, for example, production of the Higgs. You have two particles, and together they create the Higgs. Now at this triangular point here, you are dealing with the coupling of those particles to the Higgs. You can also, once you have produced the Higgs, you can study its decay. There again, at this triangular point, you can study the coupling of the Higgs to that particular particle. Any small deviation from the theory on these couplings is a messenger for new physics. And here you see just a simple result of a simulation of study of these couplings at CLIC. So here you see the particle mass of the particles that we know, which are depicted here. And here is the coupling to the Higgs. And you see this linear dependence. You can also see that this is a logarithmic scale. So that tells you that the masses of the various particles can be very, very different. And it's a challenge to study all these things in one environment. Then particles are given mass through the Higgs field, the so-called Higgs field, generated by the Higgs particle. The Higgs field is everywhere and helps to generate mass to the particles. And the Higgs field can in fact only be measured in the so-called Higgs self-coupling. And this is a diagram like this one, but this time the Higgs disintegrate in two other Higgses. The probability for this reaction is extremely low, and it will be difficult to measure at any collider. But CLIC currently offers the best perspective for this measurement in a given luminosity, so in a given scenario of a number of years of measurement. So coming back to electrons and protons, so here you see a cartoon of a proton. The proton is composed of 3 quarks that are held together by gluons. So the proton, in fact, is not an elementary particle. This is different for the electron and its antiparticle, the positron. Those are real elementary particles to our knowledge. So as Dr. Steinar Stapnes described, the accelerators that we can build best are in fact proton and electron accelerators. Now if you generate proton-proton collisions, then you in fact generate collisions between, for example, 1 quark of 1 proton and a gluon of the opposite proton, or an interaction between two quarks or two gluons. But in fact, when the interaction takes place, you don't know which fraction of the mass is carried by that particular quark, because as you see, it changes all the time. So you don't know the initial state of the reaction very good. And this limits your achievable precision. This is different for electrons and positrons. As they are point-like, the initial state is actually defined by the accelerator itself. And you can even give them a polarization. So this allows you to do high precision measurements. Then protons have very high rates of interactions of a particular type, mostly the strong nuclear interaction. And this, I will come back to this on the next slide. And this forces you to be very detailed in finding the interesting interactions in a huge heap of more standard interactions. And this then also leads to high levels of radiation in your detectors. In electron-positron colliders, your environment is much more clean. You don't need to search so much, and you profit from lower radiation levels. Protons have high cross-sections for colored states, so for strong nuclear interactions, whereas electrons have superior sensitivity to other interactions, electroweak interactions. So the two machines are really fully complementary. Okay, so just to illustrate a little bit more the difficulty of doing experiments with proton collisions, is you have here a plot of cross-section. Cross-section is in fact probability that an interaction occurs. On the vertical axis, you have the cross-section, and on the horizontal axis, you have the collision energy. Please note the logarithmic scale with many, many orders of magnitude. So if you have a proton interaction, the total probability for interaction sits here, whereas the Higgs production sits here. Then, if you look in detail, you have a factor of more than 100 million of probability difference between the two. So this makes your experimentation in proton collisions more difficult. If you compare it with the electrons, so again here, you have probability, it's a somewhat different scale, and collision energy. And here you see the main interesting interactions, mostly with Higgs and top particles. They sit here. And the largest cross-section process sits here. The CLIC energy range is here. And you can see immediately, while these most frequent Higgs processes are here, so you can see immediately that it's somewhat easier to do an experiment at CLIC and that the events will be more clean. Now, what physics do we want to do at the CLIC E+ E- collider? We want to do accurate measurements of known physics. This can be the Higgs particle or the top quark, which is in fact the heaviest particle that we know of. It was discovered in the United States in proton-proton collisions in 1995, 1996. And it has only been measured in proton collisions. We never had the opportunity to have an electron collider with enough energy to study the top quark. Then, of course, we want to search for new physics. We want to look for direct searches. Are there new particles being created in our new accelerator? And we can study through indirect searches by studying some processes to very high accuracy. Now, if you then make, again, a plot of cross-section versus collision energy, then you can see that it can be very advantageous to build and operate the CLIC accelerator in 3 steps. If you start at this center of mass energy, 380 GeV, then you can study accurately some of the Higgs physics and top quark physics, and you can look for new physics to see whether it exists already at that energy. Then you move up to 1.5 TeV, you can start measuring this famous Higgs self-coupling, which is related to the Higgs field. You have good chances to do further studies on top quarks and even study the coupling between the top and the Higgs, and again look for new physics. And then you build your final accelerator with 50 kilometers length and continue your searches. Now, if you then look at the implementation, as Steinar Stapnes has shown it already here, then you can see with these various center of mass energies, you see the lengths of the facility, 11 kilometers, 29 kilometers, 50 kilometers. So you can make an upgradable facility. And the number of Higgs events that you create in approximately 4 years is 100,000 to about 1.5 million. I will now give you a short introduction to particle detectors, because of course you have to measure the interactions. Particle detection. So many of the elementary particles that we know have actually very short lifetime. So not all of these particles that I showed you in the initial diagram can be measured directly. Many of them, as they are created, they almost immediately disintegrate. And they disintegrate into a small number of known particles. So for example, the Higgs, we will never see it directly. We only see its decay products. Same for the W and the Z and many more. And in particular, all the quarks that we have, they hadronize, which means as they are created, they immediately disintegrate in a wealth of particles. And they give some kind of shower of particles immediately, which we call a jet. Here you have an example of a jet. But then sometimes inside such a jet, you can have another decay, which takes place just a few millimeters after its creation. And we use this to try to learn more about the interactions. Here you see some image of a jet. Now the whole trick of our trade is to reconstruct the original particles from the visible decay products. And this is the key ingredient to our particle detectors. So particles, we cannot see them. Even with the best microscope, they are so small, we will not be able to see them. But as particles travel through material, they will leave a tiny little signal, extremely small. This can be little ionization, or some atomic effect, or nuclear effect, but in any case, it's very small. Different particles behave in a different way when they interact with matter. And that we use to make our kind of trick box to understand which particles we are actually observing in our detector. So for example, if you take a photon and you send it through your detector, and we naively just make the detector of a device that we call the tracker, which just measures a number of points where a particle has passed, which shows you in which direction the particle is leaving the interaction, but also how much momentum it has, how much quantity of motion it has, because we will apply a magnetic field here. And then we follow this tracker by two types of very heavy passive-active sandwich structures in which the particles start disintegrating. But they all disintegrate in a different way. And so it helps us to understand who is who. And then there is even a last part, which is a kind of crude detector, but it helps in understanding, as you will see. So if you take a particle of light, the photon, in the tracker, as the photon is not charged, it will not show anything. But as soon as it enters this heavy material, it will create a shower of particles that we detect in the sandwich structure. If, on the contrary, it's an electron, as it is charged, it behaves more or less like a photon here, but it leaves a trace. If you have a muon, is a different lepton, a different particle, it will just go all the way through and will leave a small signal in all of our detectors. If it's a proton or a pion, it will leave a trace and it will disintegrate, but it will disintegrate later and in a larger shower. It will just behave differently. Then if you move to the neutron, as it's neutral, it will not leave a trace here, but it will disintegrate like the proton. And then we have the elusive neutrino, which will just go all the way through your detector, and you will not detect it. But what you will detect is that you missed some energy, that some energy went somewhere and you didn't see it. So that's the way we built our detectors. Now, to do this in an optimal way, in the tracker, we want to be extremely precise in measuring these tracks. So we want this tracker to be very, very precise and extremely light, such that the particles just leave a little signal, but they don't get perturbed by material. Whereas after that, we want a lot of detection material, but also a structure that is extremely heavy. And that's the tricks we use. Now, this is not different from any particle detector. So what you see here is a cut through the CMS experiment at the LHC. Look at the scale here. So this is the interaction point, and it goes all the way to 7 meters. And it starts with the tracker, the electromagnetic calorimeter, the hadron calorimeter, the field for the magnet, just such that these tracks are curved. Then if the particle has a positive charge, it's curved one way. If it has a negative charge, it will be curved in the other direction. And then you get the muon detectors that are pretty crude. The CLIC detector will have a structure that is very similar to the CMS LHC detector. However, our detector has to be more accurate. As the collisions are more accurate, we have to keep up with the challenge and make a more accurate detector. And this is possible thanks to new technologies, and in particular, semiconductor technologies. A detector for the CLIC. So for the moment, we only have our mock-ups and our simulation models, but we are working very hard to make the best possible plans and designs, and to develop the technologies that we need to make these accurate detectors. So this is what the detector looks like, and it's just a repetition of what I showed before. So you have the electron coming from this side, the positron coming from the other side, and they collide in the center of the detector. Look at the scale here. The detector is a bit less than 12 meters long. Surrounding the interaction point, you have an ultra-low mass vertex detector with very small pixels. It's pixels like in your photo camera, but it's still a bit different, and I will tell you later. Then, surrounding the pixel detector, you have the larger tracker with a radius of 1.5 meters. And this is, again, semiconductor detectors, where the charged particles, leave a very small signal. And then we start with the heavy stuff. And that's a sandwich of very heavy material, tungsten or steel, interleaved with active material. Then the superconducting coil to create our strong magnetic field. And then at the end, the iron return yoke of the coil and our muon identification detectors. Going to the pixel detector and the tracker, they measure direction and momentum of particles and, of course, their charge. They have to be extremely accurate and light. Just to take the example of the pixel detector, it will have 2 billion pixels, 3 micron measurement accuracy, so 1/300th of a millimeter, 25 by 25 micron pixel sizes, which is 25 times smaller than the area of the pixels used in the LHC. Each individual pixel needs to measure pulse height of the signal left by the particle, and also very accurate timing to 100 millionths of a second of when the particle passed. And it has to be ultra-light. Now, the 2 billion pixels, you don't need to be impressed, because our fantastic photo cameras provide these kind of service as well. What is different in our case is that in the vertex detectors, the signal deposited by the particles is much, much smaller than the signal, the light is deposited on our photo camera. Moreover, we need individual, complete electronic signals, chains for each individual pixel, while your photo camera generally deposits a picture on the pixel array, and then the image is read out sequentially, line by line and column by column. We cannot do this. We have to have a full electronic signal circuit for every pixel. So the technologies involved are very thin silicon sensors, extremely thin, which gives you a very low signal, full electronic circuit per pixel, ultralight power delivery and cables, if not you put too much material, ultralight supports, and they should be stable with air cooling just to carry the heat away of the electronics. This is high-tech R&D. It covers many disciplines, and it has spin-off to other fields. So here I put just some images of what we are doing. So we're testing all kinds of semiconductor technology to see whether we can make the pixels smaller and smaller and thinner, and measure still with very high accuracy, without these devices dissipating a lot of heat. Because if they dissipate a lot of heat, we have to cool. And to cool, you need tubes and liquids, and this is all too heavy for our purpose. So we do many, many tests and simulations and designs to push the technology to what we need. Quite a lot of the requirements for CLIC have been achieved one by one, but our challenge is to put all these requirements together in one device. And we are not yet there, but we have time. So we work, for example, also on interconnect technologies, powering with power pulsing, turning the power on and off 50 times per second just to save on heat dissipation, telescopes to test these particles, very thin devices for support. So these studies are done in Valencia, like these ones and this one, to look at very thin supports and see how we can manage the construction of this extremely accurate and extremely thin detectors. And this is an air cooling test device. Now, our work also provides some spin-off. So this is an image of an astronaut working near one of our pixel detectors, a pixel detector that was developed for linear collider tracking applications. It was developed around 2007 or so. And this detector is now used in many applications: radiation monitoring at accelerators and in space, material science, so X-ray imaging, mass spectrometry and proton research, beam and radiation dose monitoring and hadron therapy. So the technologies that we develop, we do an effort to make sure that society profits from them. Here you see the little CERN logo on the device. Calorimeters have to be very heavy, so we need sandwiches which have heavy material, active material, heavy material, active material. We do this in about 60 layers, and this will become very heavy and compact, and will give us about 80 million readout channels. So that's 400 times more than at the LHC. Here you see the size of the devices we are testing in our test beams, and the kind of images of these showers that the particles create in this material, how we can detect them and then analyze them. So what we really want, I talked about the jet originated by quarks. This means that you have many particles very close by, whereas the particles are very often closer by than the extent of their showers in the calorimeter. Now, if you have very detailed information, you will be able, with the information of the calorimeter and very powerful software programs, to really detect every individual particle here and get the best out of your measurement. This was not yet possible at the LHC because the technologies didn't exist, but now they exist, and this is tested on a large number of prototypes. And here you see just some examples of the tests that are being carried out with different active materials, with different passive materials, to see how we can do this at best and how also we can keep the cost at a limited level. Now, the work was done for the linear colliders, but meanwhile, the LHC is looking into upgrades of their detector. And this is, again, an image of the CMS detector in open position, and this is their forward calorimeter. This calorimeter, after 10, 15 years of operation, will have too much radiation damage and will need to be replaced. And CMS has now decided to look at the technology that was developed for the linear colliders and use it in their upgrade. So it's another example of spin-off, although it's in our own field. Now a little snapshot of how well we can do the physics at CLIC with those detectors. So again, a plot of probability against center of mass energy with different processes involving the Higgs with the large H. Now there's one process that is extremely favorable and is very well known, well used in future E plus E minus colliders, and it doesn't even require the highest center of mass energy. This is the so-called Higgs strahlung. So you have the electron and the positron. They create a Z particle, and the Z particle just radiates a Higgs. Now, as you know this very well from your accelerator, and as you can measure this in your detector, in fact, you don't need to look at the Higgs. You can just see the Higgs by looking at the Z only, because you see there's something missing in your interaction. And then you try to measure that and see what you get. And this provides you model-independent Higgs measurement. You don't need to assume anything about the Higgs, and yet you can see it. And you can see this invisible Higgs decay to 1% accuracy or better. And that gives you this plot here. So this is number of events and the kind of missing energy, the missing mass in your detector, where you have some background, the signal, and the combination of the two is here. Now, maybe if you remember the plots of when the Higgs was discovered at the LHC, this was by far not such a beautiful plot. It was a huge background with a tiny, tiny signal on top that could well be analyzed statistically. But here you can reach much higher accuracy. So if we then take several of these interactions together, here it's Higgs production, here it's Higgs production, here is coupling of the Higgs to the top, at the different energies at CLIC, then I display here the projected accuracy of the coupling. And this line here corresponds to 2.5% accuracy. And here you have the total probability of interaction, and then the different known particles coupling to the Higgs. And you can see that many of them in the full CLIC program can be measured to better than about 1%. And if you compare with what the LHC can do, I put this in a color code. So if the color code is green, the accuracy will be significantly better than in the upgrade of the LHC. If it's orange, the accuracy will be comparable to what the LHC will do. Then the famous Higgs coupling, where Higgs is created and two Higgs and decays into two Higgses. This gives access to the understanding of the Higgs field, which is extremely important for our theory. This measurement can be done to just 10% accuracy at CLIC, but this is better than most other options. So here you see some images of interactions here in our detector. So here you see E plus E minus, two Higgs and two neutrinos. The neutrinos you will not see. The Higgs will decay to two B quarks. The two B quarks give you jets of particles that we can reconstruct in the detector. You can also see that this interaction is just not balanced. Normally, if you make an interaction, you should get the particles in opposite direction. The fact that the particles go in one direction means there's other particles that you don't see that went in the other direction, and those are the neutrinos. Similar, this is an event where you measure the coupling of the Higgs to the top quark, and this is a much more complicated event. It has at least 7 such jets, but you can see, you can kind of recognize, and you can imagine that if you have powerful reconstruction programs, you will do very well in reconstructing this. Then other physics at CLIC. So I mentioned the top quark. So the top quark mass is now known to 1 factor in 400 or so at present. And we can do this much better at linear colliders by looking at the probability of creating the top mass as a function of energy. Also, we can see whether, for example, the Higgs has neighbors. Does it have partner particles which are heavy? If they would exist, and within a certain mass range, we could detect them very accurately at CLIC. Then our collaboration. So the CLIC Detector and Physics study is a collaboration hosted by CERN. It has 27 institutes from 17 countries, and you see them displayed here. So we focus on CLIC-specific studies, so physics prospects, detector optimization in simulations, and detector technology R&D, as I showed. We do this in close cooperation with other projects. We don't do this in isolation. It just doesn't make sense. Particle physics needs many of these advantages, not only for CLIC, but also for other projects. So we do this together with LHC upgrades, with the International Linear Collider, which is also a linear E plus E minus collider, which was mentioned by Dr. Juan Fuster and by Steinar Stapnes, and also the Large Circular Collider that is being studied at CERN. Now, within CLIC-DP, we have a Spanish participation. It's the so-called Spanish National Network for Future Linear Colliders, which is a very nice effort to team the effort within Spain for these colliders and make sure that once these detectors have to be built, Spain can offer to participate together in one particular field. Now, many institutes are involved in this network. I have listed them here. The Spanish groups are experts on top physics. There's quite some work done in theoretical physics. Then in detector hardware, there's detailed work on silicon detectors, tracker mechanics, and pixel detector mechanics, but also in fine-grained calorimetry. That brings me to the end of my part of the presentation. Of course, I would not be able to show all this without the participation of these young guys that work in our team. Now, be reassured, we don't have a prescribed costume for people working on this study. This photograph was taken at the occasion of the yearly race around CERN, where people run in an estafette. I now hand the word again to Dr. Steinar Stapnes, and I thank you for your attention.
So I will be short, I promise you. It's been a long evening, and I will now, but what I would like to say a little bit about is how the technology, the accelerator technology, can be used in other projects. And I will show some examples of that. And I think that also has some interest, in fact, for Spain, as you will see. So one, I mentioned the rings like ALBA, which is used for creating light to study material, pharmaceuticals, for studies of in many different fields. This is called the third generation light sources. But the trend today in many countries around the world is to consider what they call fourth generation light sources. And some of them are already operational, and several of them are in construction. And the key for these, of course, is to make them smaller, cheaper, and more performant. And of course, the CLIC technology offers the potential of doing that for some of the key parameters. So a light source is basically a linear accelerator. So it has a source, you accelerate the particles, then you wiggle the particles in the magnetic field, oscillating magnetic fields, and you create laser light. And then you build experiments behind that to study different objects. And here's an example from one of the first machines of this type at Stanford, at CLIC, where you see that the studies here is not only in particle physics. There's some in physics, but there's a lot in what is called life sciences, chemistry, materials, instrumentation, engineering, optics, earth and environmental science. And I'm sure the discussion will come at some point in Spain. You have a light source of the third generation, should you have a light source of the fourth generation as well. So of course, if you look at this different light source, this is the same one from Stanford, which is several kilometers long. Here you see one in Switzerland, which is now down to something like 700 meters. And here you see a concept from Shanghai, where they have a third generation light source. They're considering a fourth generation light source nearby, but they only have 580 meters available, both for the accelerator and the experiments. So the key here is to get, and in fact, these are all based on these copper structures, but they operate at different frequency. And the push here is to go more compact, get the price down, increase the repetition rates, and make short pulses, which is right in the ballpark of the CLIC technology. So we try to work with all these, and in fact, these are collaboration members. All these three are, in fact, collaborations members of CLIC, where we work together with them. And in fact, these are also provide a lot of feedback to us about the technology. Here is a really small accelerator. So if you want a very small light source, this is what is called a tabletop accelerator, where you have a tiny little accelerator and you collide it with a laser beam, in fact, in this box behind here. So you have a small linear accelerator, you have a laser, and then the electrons will kick the photons forward, and you get an X-ray pulse. And in fact, we have several collaborators. This picture is from Tsinghua in Beijing. It's a very powerful and efficient group, and they have such a facility in their facility, such a facility at the university. This is something a university can afford and build. And in fact, there is such a project in Holland, and the main purpose of the one in Holland is to inspect pictures, like the beautiful pictures you see around here, to see are these really true pictures of the master, is there something behind, or are they false? So the museums in Amsterdam are very interested in this type of development. medicine. There is a push in irradiation, cancer treatment, where a lot of the irradiation is based on X-rays, to use protons and carbon. So this, if you see, this is water, and this is energy deposition of particles in water. And you see for X-rays, it goes up to a little bit, and then it drops off like that. Which means if you send that into the body, and the tumor is at this depth, most of the energy is deposited not where it should be. It's deposited outside the tumor. So they compensate for that by shooting in gamma rays from, shooting in X-rays from different angles to create maximum irradiation in the tumor in this particular case. You can use protons, or in fact carbon ions are also very efficient, or even more efficient in some ways, but very difficult to deal with. And then you can, with 4 beams of protons in this case, you can save this area around in a much better way. And I've taken one slide, which is in fact from our collaborators in Valencia, where they are studying using, putting an entire LINAC like that, a linear accelerator, on a rotating arm. So this will be the patient, this will be the beam, and the big instrument, which is called a gantry, rotates around the patient and shoot in protons from different directions. And this work is also being done for, in a different study, but by the same group, for carbon ions. And one of the reasons why the Valencia group is involved in the CLIC is in fact to be able to have full knowledge about this technology, and they make a big contribution to our project, but also to be able to build up their own test facilities for this type of projects. Now, so this was 3 examples of accelerators where pushing, compactness, and price are the key elements. That's really the reason why you would implement such a system or not. CLIC is not alone pushing the linear accelerator or linear collider idea. There is a long-standing project called the International Linear Collider, which is in some ways similar. It has an electron and positron, has damping rings, and so on, and has the accelerating parts. There are some differences. Here you see the parameters for that. The main difference, and the implementation considered for this project, is in north of Tokyo, in the northern part of Japan. And the Japanese government are in the process of evaluating this project. The main difference is in the what is called the RF or production of energy for acceleration, where they use a superconducting technology, which is roughly 1/3 of the accelerating gradients of CLIC. So this you see for 500 GeV, they will need 30 kilometers. So this means that this machine is perfectly suitable and comparable to a CLIC first stage. But as you go up in the energy, you run out of possibility to go to such a high energy with this technology. So we have to see if Japan is going to implement this, and of course we have to see from LHC how important is it to go to higher energy. We believe it's very important, but of course we will know quite a bit more in 5 years' time about that question, or even before, I imagine. So now, how could one implement CLIC? Can it be done? Can it be afforded, and so on? So the strategy coming from the current CERN director is quite clear. This is the roadmap for CERN, which is encompassing the community in Europe as much as possible. So the key is to exploit LHC, upgrade LHC with a high luminosity and so on. Then there are various other programs. But then the preparation for CERN Future is accelerator R&D in a number of technologies. There are design studies for CLIC, for FCC, this large ring based on protons. And in fact, I think the next talk of this type will be related to FCC. And there is also a possibility, in fact, to replace the magnets in the current LHC machine with higher field magnets and go up in energy that way. And of course, the key to all that is the results from LHC. What do we see at LHC beyond Higgs and top? Is there anything? if there's something, what energy is it at, how can you produce it in these machines, and study in these machines. So what we are doing in the meantime is the technical development. So this means that we are doing all the technical development of all these different parts and testing them in smaller accelerator setups. And of course, this is only a sample of what I've talked about. And our timeline is something like that. We are in the development phase of this project. Around 2019-20, when LHC is taking a break before further upgrades, one will have to evaluate the LHC data and the project plans for CLIC and other potential projects and make some kind of decision, if we can. We hope to be able to make some kind of direction for the future at that point. If the direction is to push on with CLIC and maybe increase the momentum for CLIC, we still need 4 to 5 years preparing before we can really go and construct such an accelerator. And one key element is to make sure that industries who have to produce thousands and thousands can really produce thousands and thousands of these elements for an accelerator. And then we can start constructing in 25. We need something like 7 years to construct. We need a couple of years to tune the accelerator, getting it up to speed. And we could be ready in 2035, which is exactly the time when LHC is foreseen to complete this program. So clearly I haven't talked about money, I haven't talked about other difficulty items like that, but we try to make this scenario for the initial stage of CLIC, so this is the 11-kilometer, compatible with LHC projects in terms of cost and the budgets we have at CERN and in Europe for particle physics, so we don't try to imagine that we have an enormous increase beyond what we have today. And that, I think, was what I wanted to say. And again, thank you to you for listening to all these words and looking at all these slides, and to the collaborators, because obviously, as Lucie pointed out, this is a work by many collaborators who also prepared the pictures and the slide which we have shown here today. Thank you.